This video is made for the Growing Science YouTube channel. Slide 1. Introduction to Golden Section Search. Welcome, everyone. Today, we are diving into the Golden Section Search, which is widely considered an elegant and highly efficient method for one-dimensional optimization. What makes this technique so fascinating is its simplicity and power. We are essentially uncovering a strategy to pinpoint a function's minimum using the fewest steps possible. The real beauty of this approach lies in its independence. Unlike many other optimization methods, the Golden Section Search works effectively without using derivatives. This makes it an ideal tool for functions where calculating a derivative is difficult or computationally expensive. Over the next few slides, we'll look at how we use a specific geometric ratio to narrow down our search area with surgical precision. Slide 3. A clever strategy, symmetrical reduction. Now let's look at the mechanics of how we actually narrow the search space. We use a predictable three-step process called symmetrical reduction. First, within any given interval, we place two interior test points, which we label as lambda and mu. Once these points are set, we move to step 2, evaluation. We calculate the function's value at both points. The third step is where the magic happens, compare and eliminate. By comparing these two values, we can logically discard a portion of the interval where the minimum simply cannot exist. Case 1. If the function value at the left point is greater than the value at the right point, the valley must be to the right. We discard the leftmost section. Case 2. Conversely, if the value at the left point is smaller, the minimum must be to the left. We discard the rightmost section. But here's the key insight for efficiency. If we are strategic about where we place these points, we can make it so that in the next step, one of our old points actually becomes one of our new test points. Slide 2. The challenge, finding the minimum efficiently. To understand why we use this method, we first have to define our objective. Our goal is to find the minimum value of a specific function within a starting interval. You can review the specific function notation and the starting boundaries on the slide. As you can see in the graph, we are working with a unimodal function. This is our key assumption. The function has exactly one valley, ensuring there is only one unique minimum, lambda star, to be found. Now here is where the challenge gets interesting. We are operating under a strict constraint. We cannot use calculus. Derivatives are off the table. Our only tool is direct function evaluation, calculating the function's value at specific points. Because each evaluation can be costly, we face a core question. How can we strategically choose our test points to shrink this initial interval of uncertainty as quickly as possible? We need a logical way to squeeze those bounds until the minimum has nowhere left to hide. 4. Deriving the magic number 1. To turn our strategy into a repeatable algorithm, we need to formalize how we place our points. We do this by introducing a ratio, alpha, which is a value between 0 and 1. You can see the specific relations for calculating the left and right interior points in the formulas on this slide. Now let's apply our efficiency goal. Suppose we discard the left portion of our interval. We want to reuse the point we already have. Specifically, we want the old right point to perfectly align with the new left point in the very next iteration. By doing this, we eliminate the need to calculate a new function value for that position. If we look at the algebraic goal at the bottom of the slide, we are looking for the specific value of alpha that makes this reuse possible. In the next slide, we'll reveal the magic number that results from this logic. Slide 5. The golden ratio revealed. Now, let's follow the logic to its conclusion. We start with our desired efficiency condition. We want our current right point to become the next iteration's left point. When we substitute the formulas for these terms, as shown on the slide, a beautiful thing happens. By simplifying the expression, all the complexity collapses into a remarkably simple quadratic equation. Solving this equation gives us a valid solution for alpha of approximately 0.618. This value is the golden ratio, specifically its reciprocal. It is the only ratio in existence that ensures a perfectly symmetrical overlap between iterations. Because of this unique mathematical property, one of our existing points can be reused in every single step. We have effectively cut our future workload in half while maintaining a constant, predictable rate of convergence. Slide 6. The Golden Section Search algorithm. Now that we've seen the foundation, let's look at how this functions as a complete algorithm. The process is divided into an initialization and a main loop. Phase 1, initialization. First, we set our boundaries and choose a tolerance level, which is our final desired length of uncertainty. We set our magic ratio, alpha, to 0.618 and calculate our first two internal test points using the relations shown here. Phase 2, the main loop. Once initialized, we enter a loop. At the start of every step, we check the current interval width. If it is smaller than our tolerance, we stop. The minimum is found. If not, we compare our function values. Depending on which value is larger, we shift our boundaries and reuse one of our existing points as either the new left or new right point. This means we only need to perform one new evaluation per loop. As we continue, the interval of uncertainty shrinks by approximately 38.2% in every single step. Slide 7. Example. Putting theory into practice. To see the search in action, let's walk through the first iteration. We start with a current interval of -3 to 5, giving us a total width of 8 units. Our goal is to minimize the quadratic function shown on the slide. Step 1. Using our golden ratio, we find our two interior test points. You can see the specific calculations resulting in points at 0.056 and 1.944. Step 2. We plug these points into our function. The first point gives us a value of roughly 0.115, while the second gives us a much higher value of 7.667. Step 3. Comparing these, we see the first value is much smaller. This tells us the minimum cannot be on the far right side of the interval. Step 4. We discard the entire right-hand portion. Our new interval is now -3 to 1.944. For the next iteration, our current left point will automatically become our new right point, as shown in the diagram. Slide 8. Example. Iteration 2, the efficient way. Now, let's look at the second iteration where the efficiency finally pays off. We start with our new, smaller interval. Step 1. Because we use the golden ratio, we don't start from scratch. Our old left point from the previous step now perfectly aligns as our new right point. Crucially, we do not need to recalculate the function value for this point. We already know it. We only need to find one brand new left point, which calculates to -1.111. Step 2, we perform just one new function evaluation, which gives us approximately -0.987. Step 3, comparing this to our reused value, we find the new point is even lower. Step 4, once again, we discard the right-hand portion of the interval. In just 2 iterations, we have narrowed our search width from 8 units down to about 3 units, using only 3 function evaluations instead of 4. This efficiency continues forever. You can read the last 3 slides to better understand why this method is so effective and widely used in optimization, and thank you very much for your time and attention throughout this presentation.